Welcome back to Advent of Code 2022, day 14. John Eisen. Hope you guys are enjoying these videos. If you do, like them, subscribe them, comment, I don't know, do all that stuff. Let's get started. The regolith reservoir. The distress signal leads you to a giant waterfall. Actually, hang on. The signal seems like it's coming from the waterfall itself, and that doesn't make any sense. However, you do notice a little path that leads behind the waterfall. Correction, the distress signal leads you to behind a giant waterfall. There seems to be a large cave system here, and the signal definitely leads further inside. As you begin to make your way deeper underground, you can feel the ground rumble for a moment. Sands begin pouring into the cave. If you don't quickly figure out where the sand is going, you could quickly become trapped. Fortunately, your familiarity with analyzing the path of falling material will come in handy here. You scan a two-dimensional vertical slice of the cave above you, your puzzle input, and discover that it is mostly air with structures made of rock. Excuse me. Your scan traces the path of each solid rock structure, reports the XY coordinates to form the shape of the path, where X represents the distance to the right and Y represents the distance down. Each path appears as a single line of text in your scan. After the first point of each path, each point indicates the end of a straight horizontal or vertical line to be drawn from the previous point. For example, 498.4, 498.6. So down 2, 496.6, over right 2. Scan means there are two paths of rock. The first path consists of two straight lines, and the second path consists of three straight lines. Specifically, the sand is pouring into the cave from point 500 0. Drawing rock as pound and air as dot, the source of the sand as plus, this becomes 500. Here's the source of the sand, and there's rock here, and there's rock here. Okay, sand is produced 1 unit at a time. The next unit of sand is not produced until the previous unit of sand comes to rest. A unit of sand is large enough to fill 1 tile of air in your scan. Okay, so 1 unit at a time, and then 1 unit, and then 1 unit, then 1 unit, then 1 unit. And eventually it'll get here, and then I guess it'll spread out. A unit of sand always falls down 1 step if possible. The tile immediately below it is blocked by rock or sand. The unit of sand attempts to instead move diagonally 1 step down and to the left. Okay, so if once this unit is blocked, it will move here. If that tile is blocked, the unit attempts to move diagonally 1 step down and to the right, and then it'll move here. And then sand keeps moving as long as it's able to do so, at each step trying to move down, then down left, then down right. If all 3 possible destinations are blocked, the unit of sand comes to rest and no longer moves, at which point the next unit of sand is created back at the source. So drawing the sand as it comes to rest as an O, the first unit of sand essentially falls straight down and then stops. Okay, so you don't do it 1, 1, 1, you just go all the way down. So it's like Tetris when you hit the down button, right? And then we go here, and then eventually, then 22, okay. Oh, so it doesn't go left out, right? According to those rules. Finally, only 2 more units of sand can possibly come to rest. Oh, because everything else flows off the side. Okay. All right. Using your scan, simulate the falling sand. How many units of sand come to rest before the sand starts flowing into the abyss below? Very interesting puzzle. Okay. Let's take a look at this input, because I think it's really gonna imply how we structure this problem. So I'm seeing a lot of numbers starting with 4. It looks like this is like 400, 500. This is at most a 200 by 200 grid. So let's first read in the input, and then we're going to do a little bit of analysis here before we design a solution. So first let's read in this input, right? So we have each line creates a rock path. Rock path is a list of vertex. A vertex is a tuple int, and our paths rocks are a list of rock path. Okay, and we do rocks here. Def parse rock, line, string, rock path is going to do with line.split on space arrow, and we're going to do parse vertex on S for S in line.split, return, and parse vertex, def parse vertex on S stir to a vertex is return xy equals s.split on comma, return int x, int y, and we just do parse rock path here. Okay, so that returns our rock path. Now, the first thing I want to do is I want to print the minimum value of x and the minimum value of y and the maximum value of x and the maximum value of y, because I want to know how big this matrix has to be. So min x equals min of x for x comma underscore in rock path for rock path in input.rocks. And we're just going to do this for all max x okay, and we're going to print min x, min x, max x, max x, okay, and I'm going to run this Python day 14 example 494. All right, so this works for the example, and we're doing it on the input. Okay, so all right, we only go from x 486 to 571, and y, well, y starts at 0 because we know 500 zeros in the, and to 171. That means that we only have, what is this, a 85 wide, 171 deep matrix to handle. So I think we can just draw the paths and then run our algorithm as just like walking it down and following the rules. Like, I don't think we need to represent it as any like fancy lookup. We can just put it in a big matrix of that size because that's just not big enough to really cause us to have to do anything special. Now maybe part 2 will make us have to do something special, but until then, let's just do this straightforward like. So we know the min y is 0 actually, because we're going to start at 0 because it's 500 and 0. Okay, so what we're going to do is do matrix equals we're just going to draw it like they do, right? Let's make an enum. Class location, class what do we want to call this thing? We call it a location, whatever. I don't know. I don't know what to call it. But it's going to represent, it's an enum of empty, source, rock, or sand. Okay. And then our matrix is a matrix of this. So what we are going to do is we're going to make a matrix of dot for underscore in range. So X is going to, so the outer matrix is going to be, each row is going to be Y. So the inner matrix is going to be X. So we're going to do range max X. We're going to do 0 to max X minus min X. And we're going to do the inner matrix for range in 0 to max Y minus min Y. Okay, and we're going to put dots in all those. We're going to do matrix of def set xy is matrix of, now y is the outer, so y minus min y, x minus min x equals val v. We'll call it a value. I don't know. It's a thing. Okay, so set will set the matrix value, and we'll do define get x int y int return value equals return matrix y minus min y, x minus min x. Okay, cool. So now we've set up a matrix and we've made some getters and setters. We can remove this. So now we just let's just draw all the rocks in. So for rock path in, let's do class, let's just what is this called, this map called the rock map. All right, so now we're handling this. We're going to do self dot on all these. We'll call this the map. Self.map, and then we'll do the set will be here, and we'll do self, 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 self. Right, okay, and then we'll do set, and it's going to be x500 y0 is value dot source, and we'll also set self dot source equals 500 0, so we can reuse that later. And then for rock path and input dot rocks, self dot draw. Oh, and then for each rock path, for v1, v2 in zip rock path 1 colon. So what this does is it gives us each pair of vertices. We're going to do self dot draw v1, v2 value dot rock, and yeah, actually this has to be value dot empty. Okay, so what we're gonna define this method self.draw right now. Def draw. It's gonna draw from one vertex to another. In the map. So for x in v1 0 to v2 0, if v1 0 not equal v2 0, then x1 equals v1 0 and x2 equals v2 0, and for x in range x1 min of x1 x2 to max of x1 x2 plus 1, self.set x y equals v1 0. So we never do a diagonal path, so we can just do it like this: set x y v, and else do similarly for y. So this is going to be y1, y2, 1, 1. This is going to be x. This is going to be y. I said x, y, v. Yep. Okay. Self.draw. All right. So that self.draw should work. So now we've drawn every rock path. So now we should print our matrix. So let's make a string method. Def self print x boundaries self.min x do the same thing for y, and print new line dot join empty dot join v dot value for v in line, and we'll call this row, for row in self.map. Okay. All right. So map equals rock map input print map. Oh, yeah, sorry. We want to do return plus okay. All right. Let's do self here. Self. We're missing all our selves. Index is out of range. Well, shucks. Maybe it's a +1 here and a +1 here. Okay. All right. X boundaries. Oh, that doesn't look good. We go 494 to 503 and 0 to 9, and we draw the exact same map. Cool. All right, well now let's fill in the map. So we should just drop sand. We should just make a drop sand method. Drop sand self. Okay, so now we just have to we have to follow the rules to drop the sand. So we'll just do while true. Maybe we'll replace it. Sand equals self.source. We'll do xy equals self.source. Okay, and then we'll just start going down, right? If self.get x, y plus 1 is down, we'll do down here and down left, then and down left equals self.get x minus 1, y plus 1, and down right x plus 1. If down is equal to value.empty, y equals y plus 1, and continue, like keep going, yeah? Otherwise, if down is anything else, wait, hold on a second. I want to make sure we don't get out. Our get function should handle if it's outside of the map. So let's do abyss. So if it's outside the map, we just call it abyss. If x is less than self.minx, or actually we can do this, self.minx less than, or if x is greater than self.maxx, or y is less than self.min_y, or y is greater than self.maxy, return value.abyss. Okay. So if down, so what's the rules? Let's start with these, let's reread these rules. You always falls down one step if possible. So if down is value.empty, we fall down one step and continue. If the tile immediately below is blocked by rock or sand, which are the only things that it could be. All right, so otherwise, then, so elif down in value.sand, value.rock, instead move diagonally one step down and to the left. All right, so then we do if down left is value.empty, then y equals y plus 1 and x equals x minus 1. Then we set it to down left and we continue. If that is else, if down left is blocked, and we have to handle the abyss cases as well here, but I'm skipping those for now. I'll come back to those. So if that is blocked, then we try down right. So if down right equals value.empty, then x equals x plus 1, y equals y plus 1. Continue. And then if it's blocked, elif down right in value.sand, value.rock. We got to do something here. We do else, abyss, pass, else, abyss, pass, and else, abyss. So what do we do for these three abysses? I believe if it's an abyss, then it's going to keep moving down, but it's keep moving down forever. So if it's an abyss, then we want to return union of value.abyss. We return bool. For if it returns true, then we're ending. So if we ever hit an abyss, we return true. So whenever you hit an abyss, you return true, right? The only thing we didn't fill in is if down right is blocked. If all three possible destinations are blocked, the unit of sand comes to rest and no longer moves. Then we do self.set x, y, value.sand, return false. Because false means we need to continue. We haven't hit the abyss. Cool. I think this is actually good. Let's run it on the part one for the example and see what happens. So I'm going to print the map every single time. So we're going to do while map.drop sand 0 1 print map. While not map.drop sand. And then we probably want to do it on, yeah. All right. Okay, so we got 24 to think. Ooh, is that correct? Yeah. And is the map correct? Yeah. Huh. Okay. Cool. Let's do it on the input. 1001. We got it right. Wow. That was, I didn't expect to write that perfectly the first time, but we just followed the rules and modeled the problem well. Now, if the boundaries get really, really big and we can't, just walk a matrix, then things are going to get more complicated. So let's see what happens in part 2. Maybe they'll make us do that. You realize you misread the scan. There isn't an endless void at the bottom of the scan. There's floor and you're standing on it. You don't have time to scan the floor, so assume the floor is an infinite horizontal line with a y-coordinate equal to 2 plus the highest y-coordinate of any point in your scan. In the example above, the highest y-coordinate is 9, so the floor is 11. And the extra rock path goes negative infinity to infinity. Okay, so the example now looks like this. To find somewhere to stand, you'll need to be simulating falling sand until the unit of sand comes to rest at 500, 0, blocking the source entirely and stopping the flow. Okay, so it actually takes over the source. In the example above, the situation finally looks like this after 93 units. Okay, cool. So, very good. Now we just have to model it with a floor, so we can use the same method, but we just have to do two things. We have to increase the y, and we have to, by 2, to rock on the bottom, and we have to increase the x. Now the question is, how much do we have to increase the x? Well, it turns out that we can just look at this example and figure it out, right? So look, we start at 500, 0, 501, 502, 503. So it turns out we have to increase x by the amount of y we go down to the right and to the left. So even though x started out as 85 wide in our input, it will end up having to be, with y being 171, we're going to end up having 171 to the right and 171 to the left. So it'll be much wider. It'll be like 342 wide. So what I'm going to do is I'm going to make a little rock map part 2 class based on rock map. And I'm going to def a new init function. And I'm going to copy a bunch of this init stuff. So I'm going to do self.super.init self rock map. How do you do super class init Python? I always forget this syntax. Okay, yeah, you can just do rockmap.init self. Okay, so we're initializing the rock map, but then we want to rewrite the matrix and rewrite the self.min_y. So self.min.x should equal the minimum of self.min_x, let's calculate the y first. Self.max_y, it's now plus equals by 2. We add 2 to it. And self.min_y is 0, so then we do, and then assert self.min_y 0. Whoops. Right. And then our min_x is actually going to be 500 minus self.max_y. And do we need one more? We do need one more, self.max_y minus 1. That way, well, we'll just do minus 2 just to be sure, but I'm pretty sure you only need 1. And we're going to do the same thing with max_x. Cool. So now we're going to redraw our matrix, or map. I'm just going to copy this stuff. Cool. All right, so now we can redraw the map and just call this self.draw rock path. So we're going to reuse this thing. Okay, and yep, so we've changed self.maxx and minx and min y max y. Cool. So now we so now this rock map should still do the same thing, but it's just bigger and now it's formatted like this. So we can just grab this and this, and we need to make an extra condition in our drop sand function for what if the sand comes to rest at the source. So while self.get x self.source not on this while, but right. Well, we should just check it. If self.get xy equals value.sand, return true. So the returning true will say that it's an abyss, that the sand didn't drop. And so if we ever call and sand has already been set on the source, then we get out of there. So this should just work for part 2 and part 1 now. So I'm gonna do the same thing I did and run the example. Little bug. Okay. All right, so we just did rock map 1. So we need to do rock map 2. Try that again. Rock map 2 done it takes we have to draw the bottom line. So self.draw self.minx self.maxy self.maxx self.maxy value.rock. So we have to draw the bottom line of rock. Okay, and we got 93. It's 93. That's correct. Okay, wow. We're on a roll today. I thought this would be harder. All right. It's going to take a little bit of time, but not too long. And we got it right. Awesome. So yeah, this problem could have been way harder if the numbers were way bigger, because then you really can't draw a matrix and calculate in certain time. But I thought it was really good of us at the beginning to check the boundaries that we were working with so that we could know that that a naive solution, or like a drawing solution could work. And once we did that, it was really just pretty direct to draw where the rocks are and then calculate where the sand drops. So I thought that was awesome. And we did really well. And we even reused our code from part 1 and part 2. Yeah, I'm really happy with the solution. So hope you guys enjoyed it, and I'll see you tomorrow.